Hello, my name is Yolanda Light. I'm an associate professor at the Division of Robotics, Perception and Learning at KTH, and I'm here to present our collaborative project funded by Digital Futures with the title Advanced Adaptive Intelligence Systems. Our project has 6 PIs with complementary expertise in areas such as conversational interaction, computer-supported collaborative work, and human-robot interaction. The purpose of our project is to develop novel methodologies and approaches for developing an adaptive technology demonstrator, a smart kitchen with the ability to adapt to unknown environments and situations. Additionally, our project will also develop decision-making modules in the form of integrating physical human-robot interaction with conversational technologies that can adapt to users' needs and expectations, contexts, or actions. In this talk, I'll go briefly through some of the main activities that we've been working on during the first half of this project, so about 2 years. To better understand older adults' needs and interests in the kitchen, we started by conducting video studies with older adults cooking in their own homes without any assistive technologies. The purpose of these data collections were to investigate the complexity of these kitchen tasks and create some design principles for these assistive technologies in the kitchen to ensure the acceptability of such technologies and, of course, the needs of these users. In parallel, we've also been running a few more controlled studies in more lab environments to understand how conversational user interfaces can help users navigate through instructions, both in video or in spoken lists. In the first study that we published at CHI, we have shown how users can build sometimes wrong shared understanding of the context of interactions with the agent. These experiments were conducted actually in users' homes with voice commands to control an instructional video of an unfamiliar recipe. When analyzing these commands, we set out to see how agents could understand the context of what is being presented and understanding challenges for how these interactions can be misleading. In a second study, users also navigated through lists of instructions in a lab setting with Lego blocks with either a gaze interaction in that an agent waited until they looked up for the next instruction or using speech. The results of this work show that when things went wrong, as they were designed in such cases for the experiment to happen, it was significantly faster for people to repair a broken spoken interaction using gaze, pointing, or an opportunity. So this seems like an opportunity to improve conversational interfaces with nonverbal behavior. Building on these works, we're also working on recruiting participants for a comparative study of a cooking activity with our TEMA robot. Though here we want to test several interaction styles, and the aim is to compare young adults with those over 64. The idea is that this system will provide recipe steps on request, allow participants to request instructions or replacing some ingredients, offer them a substitution if detected, and alert participants when the recipe timings are complete. At the same time, in the physical human-robot interaction domain, we've been mostly collecting data from several thousands of human-robot handovers. And now we are actually building machine learning methods to extract relevant characteristics of these handovers. The future goal is that this physical part of the robot could be integrated also with the conversational interfaces and systems that we're building in the project, also providing both practical help and nonverbal communication. And here, in terms of adaptivity, we're expecting the robot to adapt to different users and situations while retaining characteristics from human actions. In terms of perception, we're also exploring different perception modalities that are not so well established in the literature, like vision or speech. So we're looking into thermal infrared imaging and whether that's a useful modality to improve the detection of frustration in human-robot interaction. So we've been collecting data on while participants interact with a robot in frustration situations due to cognitive overload or failures of the robot. These are typical situations that can happen in home human-robot interaction, so that's why we pick them. And after collecting this data, we actually train machine learning models to detect frustration using only thermal region or also with other modalities like vision, RGB data. And we found that thermal imaging can actually be a very good complement to these typically established modalities when detecting frustration in human-robot interaction. This was a lab data collection, but in the past year, we also put a fur-hat robot at KTH library, and we tried to collect this autonomous data of frustration in the wild. So the fur-hat robot here was acting as a receptionist, helping people find rooms at the library, but it was clearly sending wrong instructions, again, to collect frustration, but in this more spontaneous, in the wild environment. And we are now in the process of analyzing this data, in particularly trying to understand the differences between this more real-world data versus the data that we collected in the lab that is much more structured and we can control much more. In terms of adaptive speech and gesture generation, we've been working on two different directions: robot mimicry and adaptive motions and speech. In terms of robot mimicry, we've run some studies showing that robots or avatars that adapt their expression or movement can be perceived as more natural and responsive by third-party observers. And here we also ran a pilot experiment with a real-time adaptive robot. So previous research has shown this for avatars, but we wanted to see whether using a fur-hat robot, these results still are visible and whether they are actually more visible. And we have a workshop publication with this data. Another challenge is, of course, more not so much on the facial expressions, but also gestures. We've been working in the automatic generation of adaptive gestures using reinforcement learning and imitation learning. And here the goal is to create these context-aware human-like pointing gestures. And to achieve this, there's been some data collection in the motion capture lab with humans pointing at target locations, and then we're employing RL imitation learning techniques to learn these human-like pointing dynamics while trying to, of course, maximize the reward of the task, which is the precision of the pointing, so where the robot or the person would like to point at. With this, we actually have a data set of 6 hours of speech and motion capture of spontaneous monologues with an actor talking about their hobbies and daily activities. And we are using this data set for different projects related to both generation of, again, gestures, but also of adaptive speech. In terms of future work, we will continue our participatory design activities for physical and conversational interventions with older adults and caregivers. We have several connections with nursing homes and from the city of Stockholm, where we're in the process of collecting data, bringing the robots there and trying to understand the main needs of people living in those environments. Of course, with the goal of investigating the acceptance and the use of conversational physical agent in caregiving settings. Of course, one of our overall goals is to enable these more robust real-world deployments, and that's why we try to create as more realistic as environments as possible, either by collecting data actually in the real-world environments, or as we are planning for the next few years, in our Intelligence Augmentation Lab, which is a lab that is actually being built now at Linzenswegen 24 at KTH. And this is supposed to be one of the several interaction and robotics labs built in this floor. And the idea here is that we will have a kitchen and living room area with a flexible setup, but with several sensors, displays, and so on. So this sort of like smart kitchen environment that we plan to conduct the final experiments of the project in this setup and have a demonstrator with the prototype that we develop in the project in this lab. I would like to thank you for your attention. Leave the names of the PIs here, but if you want more information, feel free to reach out to us or to check our webpage the webpage of our project in the Digital Futures website. Thank you.